ఇక్కడ చూసుకోవాలి వాట్సాప్ ఏదైనా డౌన్లోడ్ అయ్యింది. Okay, very good evening, children. So now the time has came to discuss about regarding one of the maths oriented chapter, that is more so problematic oriented chapter. That's what that is states of matter. Now we are going to discuss. Already we have finished what atomic structure, and as well as we have completed periodic classification. So this is the third part, which has included a major portion in this topic. We are having mathematical part only. So along with that, some laws also we are having. So now we are going to discuss about what states of matter. So my name is Venkatesh. I am from Bellampally TRA school. This is a webinar program conducted by TRA Society. And so this is what states of matter. Actually, this was posted regarding what actually in the previous atomic structure it was mentioned on it. So the main gas laws, Graham's law and Dalton's law is molecular speeds. After that, that's the seventh concept is what surface tension and as well as what viscosity. So in this lesson, children, so problems in the competitive pattern. Laws are included with the mathematical part, and as well as we'll get some problems in the competitive pattern. Either it might be an IIT and as well as what NEET in these both the cases, and as well as MCET also. So the topics, if we'll see that the first property is what measurable properties are there. Majorly in this lesson we'll discuss about especially gas. So states of matter. Generally everybody knows that as what matter is nothing but it is defined as what whatever it will be there. And that can be in the states of what three states are there. One is what a solid state, liquid state, as well as gaseous state. We have the fourth state is the plasma state, and states of matter. Discuss about what gas is. Okay, so matter, that is what gas will. That we'll see here. The measurable properties of gases, if we'll see. So he's saying that what will fill the gas, just will blow the air into that, and just we just will compress it. What will happen? All the gas molecules which are present in that. Some of the gas enter into that piston, and as well as what when we press that piston once again to the forward direction by closing the mouth of the syringe, at that time what will happen? The piston can move somewhat forward. So based on that we can say that as what gases may be compressed. And one more thing is saying a second property is what gases expand when less pressure is applied. So when less pressure is applied, what will happen? They'll try they'll try to compress it. Okay, mixed. Yes, that we know that because if we'll see that what nitrogen, oxygen, hydrogen. So these gases, if we have taken what's these are all the gases will mix and will form some new gases. So we can say that gases may be compressed and gases can be expanded while applying a low pressure, and as well as gases can be mixed. So be mixed. But solids not be like that. Why? Because book, if both we are kept kept together at that time, what will happen? Whereas in the case of gases, what will happen? If you want to keeping those two gases together, put together, but at that time, what will happen? There is a chance of mixing of gases. So the fourth point, if we'll see, if gases exert a constant container walls will. It's saying that as what gases may exert pressure exchange because of the collidal of the molecules. When these gas molecules are collides, that means a bombardment is there with the gas molecules are bombarding with what container what we are taking. So because of that reason, what gas molecules may exert the pressure upon the walls of the containers what we are taking. Next one, the gases have a very low densities. That's what a low densities it is saying. Density is nothing but what mass by volume. How much volume is occupied by the particular mass of a gas is can be called as what density is equal to m by b. So based on that, we can say that as what gases have very low densities. And after that, I'll go with the next slide. So these are the first measurable properties of the gases. What are the properties of measure? So some of other measurable properties, if we'll see temperature, if we'll see that as what, how can we measure it and what are the units for that and in which way we can measure the property that is temperature. If we'll see temperature, we may measure in degrees Celsius as well as Fahrenheit. Degrees Fahrenheit it is there, degrees Celsius, and as well as degrees Fahrenheit it will be. Example, if we have taken Celsius and Fahrenheit are two different scales and they are used to measure the temperature. So what they want of the measurable property for the gas. What are they? One is degree Celsius and one is what a Fahrenheit. Children. Okay, so he's saying that what Celsius and Fahrenheit both are there. They are two different scales used in measuring temperature. So while the temperature can be used in two different scales, that is Fahrenheit and degree centigrade, 32 Fahrenheit is equal to 0 degrees centigrade. He's saying. So if, for example, in the Fahrenheit, it is equal to steam point of the water if you have taken. That means what two units are equal in which number it will be that he is giving. So conversion is given and Fahrenheit to degree centigrade is there as well as a degree centigrade to Fahrenheit it is there. So it is one of the formula which there may be a chance of asking of conversion of degree centigrade to Fahrenheit in Fahrenheit. Let's see 41 he's asking us what multiply and then multiply by 5 and then divided by 9 is given. That's what f minus 32 by 5 into f minus 32 we are getting the degree centigrade that is 42 degrees. So for the formula what we are getting for the Fahrenheit to degree conversion, f minus 32 into 5 by 9 is equal to that's degree centigrade. Okay, so this is what the conversion of Fahrenheit. We'll see the degrees to Fahrenheit is there. The second one is degree centigrade. He's asking. Example, we have taken 5. That's why we have taken a 5 degree centigrade. If you have taken x degree centigrade, that x degree will come here. That x degree centigrade, and it can be multiplied by 9. Fahrenheit will be. So these are the two formulas we are going to apply in order to calculate the degrees to Fahrenheit conversion and Fahrenheit. Okay, children, after that. So these are that we have discussed. And after that, you will see the table below what she has given here, and shows different commonly used units of measuring gas pressure. Use this table in the pressure of units conversion she has given. So this what temperature we have already discussed. What's that next topic? It will be what this is one of the measurable property. One is what atmosphere, so it's pressure he has given. These are the units: atmospheres, millimeters of mercury, mmHg. Generally, we can call it as abbreviation. Generally, in problems, we will use with this symbol. So these are the units of the pressure. Atmosphere is units of the pressure, millimeter for mercury, and torrs as well as inches in mercury, and pounds per square inches, and as well as what Pascal will be. So these are the pressure units. Already we discussed what in the first slide, what one of the measurable property is that's what pressure will be. And when we apply the pressure, what will happen? The gas molecules can compress, and as well as when we increase the pressure, what will happen? Expansion is there. So because of that reason, what will happen? Pressure having the gas can have the pressure in the units of atmospheres, mm of Hg, and torrs, pascals, like this it will be there. We'll see 1 atmosphere is equals to, that is what 1 atmosphere exactly, that is one of the unit of the pressure of the gas. That can be say in mm of Hg also. 1 atmosphere is equivalent to 760 mm of Hg. That is in barometer, that we know that will measure the pressure by using of a barometer. Already we learned in very lower classes. Okay, and torr is also one of the unit, and 1 atmosphere is equal to 760%. Children, you have to remember this or all. Why? Because in some cases, what in the problems in this lesson, especially he will mention as what he might be mentioned atmospheres, or might be some mm of Hg and torrs or pascals, whatever it may be. So because of that reason, what we need to remember all the units. That is very important for this lesson. And inches of mercury, if we have seen 29.9, it is there. And pounds per square is 14.7, it is there. PSI is given. And it is what pascals, 101.325 pascals, 1 atmosphere is equals to. This is what temperature is completed, as well as pressure we have also finished. The next measurable property, if we have seen, what three measurable properties now we are discussing here. One is what temperature and pressure and a volumetry. Based on these factors only, the next slides and the next lesson, next topics will depend upon these three factors. Because of that reason only, especially we are discussing these three factors. Remaining other factors also will be there, but we are not discussing. By means what? Major these three factors or impact the lesson. That's why we are discussing this. So the third unit is what, children? Volume unit. So volume units might be liters, kiloliters, gallons we can measure, cubic ad and cubic foot also. So in these many other these are the other units in order to measure the volume it will be. So if you have taken 1 meter cube, cubic meter cube is equals to 1 meter cube, it is there. 1 liter is equal to 0.001 meter cube, it is there. So conversion to liter to meter cube conversion we have taken. 1 kiloliter is equal to 1 meter cube, that is 1 kiloliter is equal to 1 meter cube, it is there. 1 gallon is equal to this much, and 1 cubic ad is equal to 0.76455 will be there. And 1 cubic foot, if we have taken, the volume is how much it is there? 0.028316 meters it will be there. So in this manner, what we are measuring the volume of a gas. For matter, major measurable properties are discussed. What we have, that pressure, temperature, and as well as volume. So in which units we need to measure, what are the units conversion, how we have to measure the pressure, temperature, and as well as volume. Okay, children. Okay, fine. Then if we'll see the next slide. So in this, if we'll observe here, what he wants to say is properties of a substance do not change with the change of its physical state. What means changing? For example, solid state to liquid state is changed, liquid state to gaseous state is changed. Properties of the substance do not change with the change of its physical state. Chemical reactions to depend upon the physical state. Properties of the substance what we have taken or the matter what we have taken, they do not change with its physical state, but they do change depends upon what the rate of chemical reactions to depends upon the physical state. By changing of the physical state, there may be a chance. So what change rate of the chemical reactions will depend upon the physical state. So the based on the physical state, the rate of reaction may depend. For example, if you have taken as what the reaction of water with other substance, the reaction with ice cube with other substance will be completely different. And the reaction of steam with other substance, it will be different. Why? Because what if we have taken what the water molecules in case of steam, in case of ice cube, in case of water, reactivity is completely different, but the properties will not change. That we need to observe there. Many times in calculations, while dealing with the data of experiments, we require knowledge of the states of matter. So in order to know the rate of the chemical reactions of different states, definitely we need to know the knowledge of the states of matter. Therefore, it becomes necessary for a chemist to know the physical laws, especially in order to discuss about the physical states of matter. We need to know some laws. It's very important in order to get a knowledge of this lesson. So which govern the behavior of the matter in different states, it will be what are those physical laws that we will see that in this unit. We will learn more about these three physical states of matter, particularly, especially liquids and gases. That means what? In this lesson, majorly we'll discuss about what are liquids and gases, especially, and the major portion is covered for the gases states only. Okay, children. After that, now, we are taking as what Boyle's law. So, what is Boyle's law? These are the physical laws we are having in this lesson. Okay, so London dispersion forces are there, intermolecular forces are there, and as well as hydrogen bonded forces will be there. So, there are the molecular, intermolecular forces. It's not a matter to for the competitive pattern. Majorly, we have to focus on the laws, especially, and after that, ideal gas equation and real gas equation. After that, surface tension and viscosity. These are the major important topics in this, and molecular speeds also one of the important topics in this. So the first gas law will be what a Boyle's law. These are the laws are applicable for the gases. That's why only we mentioned it as what gas laws. We are not saying as what liquid laws and solid laws like that. Okay, gas laws in the sense nothing but what the major portion is taken by the gases. That's why we are considering as what gas laws it will be. Okay, fine. Then you will see here. So what he wants to say is on the basis of these experiments. Whose experiment? Robert Boyle's experiment. So on the basis of Robert Boyle's experiment, if we will see that on the basis of his experiment, Robert Boyle's reached to the conclusion. So based on his experiment, he reached one conclusion. What is that conclusion? He concluded that if the temperature is constant, that is what at constant temperature, the pressure of a fixed amount of the gas. So that's what P, if you have considered. A gas is there and a gas pressure, the whatever the gas we have taken, that gas pressure will be what? This P will be. One gas is there, that gas pressure will be P. It is here, and this is at constant temperature. That means what? The temperature is not varying. It will be constant. Okay. So what he wants to say is, the pressure of a fixed amount of a gas, and amount is also fixed. The pressure of a fixed amount of a gas varies inversely with its volume. So if the volume is going to be changed, definitely the pressure is going to be changes. In which manner? In directly proportional manner. That in the sense what? If volume is increases, the pressure is going to be increases in the similar manner. Vice versa. If it is decreases, that's what the pressure is also going to be decreases. That is reduces. My means what? If the amount of the gas is increases, the pressure value is also going to be increases itself, and the amount of the gas is going to be reduced. The volume is reduced. The pressure is also going to be reduced. That's why we are getting the relation at constant T. At constant T, why? Because at constant temperature, clearly we have mentioned here. So that's why what? At constant temperature, the pressure of a fixed amount of the gas is directly proportional to with its volume. Sorry, it is given as what? Inversely proportional to should be. It will be there. That it was mentioned P is proportional to V. It is given. Okay. So I think it was wrongly mentioned. It is here. Actually, Boyle's law will be what? P is proportional to. Actually, Boyle's law is what, children? It has to be mentioned as what? P is proportional to 1 by V should be there. That is inversely proportional to. Actually, I was mentioned as what P is proportional to V will be. Just try to observe, children, here. That's what I want to change here. P is proportional to 1 by V here. Okay, no need to worry about that. Already the statement was clearly mentioned, but representation what I have given, that was wrong. P is proportional to 1 by V should be here. That's wrong. It was mentioned. Okay. Actually, when pressure is increases, the volume of the gas is going to be reduced. That's wrong. It was mentioned. Okay. No problem, children. P is proportional to 1 by V should be. It was wrong mentioned here. Might be some other, whatever the reason it will be. Okay, it was wrong. It is P is proportional to 1 by V should be here. And P is equal to K by V we are going to get. So, okay. Then PV is equal to K we should get. PV is equal to K. So that's what these are all. I'll change it. It's not a problem for that. I'll change it. So one more slide. I'll keep it for this. That's not a problem. Okay then. So P, it was clear only. P1 V1 is equal to, that's what P1 V2 is equal to P2 V1 should be there. That is PV is equal to constant we need to get. And based on that, density is equal to mass by volume. That we know that the formula. P is equal to K into 1 by V should be there. In place of 1 by V, that's what D is equal to M by V should be there now. That M into 1 by V we are going to write. So in place of 1 by V, we are going to write as what? K by P it will be. So that's what M into K by P we are going to write. Okay. So this is what density is equal to A by P we are going to get. So this is what Boyle's law. So D is equal to M by V we have taken. That's what P is equal to K dash P we have to get. So some it will be somewhat disturbance we got here. No problem. I'll change it in the next slide. But the Boyle's law, it is what clearly saying as what? Boyle's law is saying as what? At constant temperature, the pressure is inverse. How the pressure is going to be changed? The pressure is going to be changed as what? At constant temperature, if we'll see that the pressure of a fixed amount of a gas varies inversely with its volume. Really, it was mentioned inversely with its volume. It was mentioned inversely with its volume. By means what it is decreases. If volume increases, pressure will be decreases, volume increases. If pressure will be decreased, volume increase. If pressure will be increased, volume decreased will. Okay, so that is PV is equal to K, and it was mentioned correct only. P1 V1 is equal to P2 V2. This we got correct only. So actually PV is equal to K we should get. That P is equal to KV that we have written. K into 1 by V should be there. That one it is not it be there. It was, I think it was gone, but some mistake should be there. It's not a problem. Just keep one here. Otherwise, I'll change the slide. Not at all a problem. Okay, based on the Boyle's law, one question is here. What is that question? He's asking as what? A balloon is filled with a hydrogen at room temperature. So he's saying that as what? A balloon is going to be filled water with a hydrogen gas at a room temperature. Okay, it's fine. It will burst if pressure exceeds 0.2 bar. So with some pressure, it is filled. We don't know what is the pressure, but it is going to be burst if pressure exceeds 0.2 bar. That means nothing but what? If we'll increase the pressure up to 0.2 bar, actually some pressure it should be there, and we are exceeding the pressure how much? 0.2 bar. Additionally, we are increasing 0.2. Okay. If it is at 1 bar, pressure of the gas occupies 2.27 liter of volume. For example, if the pressure will be 1 bar, the gas which it is present in that, it is occupying how much? 2.27 liter of volume will be. Up to what volume can the balloon can be expanded? How much it can be? What volume can the balloon be expanded? He is asking. So we know that Boyle's law is what? P1 V1 is equal to P2 V2. And we know the law is what? At constant temperature, the pressure of a fixed amount of the gas is indirectly proportional to with its value. That is what P is proportional to 1 by V will be. So in this problem, if we'll see P, we are having what? Initial pressure and final pressure exceeding of 0.2 pressure and initial value, and so final value he is asking, that is V2, it will be how much he is asking. Okay, V1 he is given how much? So everybody, every value I'm writing here is what of the P1 is 1 bar. Why P1 is 1 bar? We have taken the initial pressure. If at 1 bar pressure he is saying, that's why I have taken P1 is 1 bar here. And P2 is how much? It is 0.2 bar. It exceeds up to 0.2 bar. It will be there. And initial value will be what? 2.27 liter. And we know the formula is what? P1 V1 is equal to P2 V2. It is there. Then if we'll see here, P1 V1 is equal to P2 V2, but we need to calculate the volume of V2 will be. Then V2 is equal to what? P1 V1 by P2, because V2 will be here and this P2 will come this side. So P1 V1 by P2 is here. So then V2 we are going to calculate. So V2 is equals to, what is the P1 value here? That is 1 bar. Already we have taken that. And what is the V1 value? Volume V1 is equal to what? 2.27 liters. And P2, which is in the denominator here, that will be what? 0.2. It will be 0.2 bar if we have taken. And finally, V2, how much we are going to get? 11.35 liters. Since balloon bursts the 0.2 bar pressure, the volume of the balloon should be less than what? How much it should be, up to how much it should be expanded is mentioned as what? We got the value. The volume will be how much? 11.35 liters will be. It should be expanded up to 11.35 liters. So this is about what? Boyle's law. So the first gas law, that is what Boyle's law will be. So the ultimate thing is what? If at constant pressure, a gas, if we have taken, the pressure of that fixed amount of the gas is indirectly proportional to its volume. That means what? The pressure of a fixed amount of the gas is varies inversely with its value. This is called as what? A Boyle's law. That is P is proportional to 1 by V. Once again, I am saying that as what? This you can change as what? P is not proportional to V. P is proportional to 1 by V should be. Okay. Just you have to change it. Guys, I'll also change. It's not a problem. Next one is what? Second law, which is the relation between V and T will be. Already we have three measurable properties along with units. We have discussed what? Pressure, temperature, and value. In the initial Boyle's law case, what we have taken, at a constant temperature, if we have seen that pressure and volumes are variable things, variable properties. But now in this case, Charles' law, what we are considering, V and T are variable properties, and what should be constant here? We'll see. So for a fixed mass of a gas at constant pressure, so PVT, if we have taken, what is constant, children, here? The pressure is constant. And what are variables? V and T are. Volume and temperature both are variables here. Okay. So at constant pressure, the volume of the gas, that's V will be here. The volume of the gas is, what he is saying, the volume of a gas increases on increasing the temperature and decreases and cooling by cooling process. That's what directly proportional relationship. Not like what Boyle's law. That is, there is an indirectly proportional relationship between pressure and volume. But here, if we'll see, if we'll increase the temperature, the volume also going to be enhanced. If we'll decrease the temperature, that meant nothing but cooling process. If we'll do, what will happen? The volume also going to be reduces. They found that for each degree rise in temperature. So that we will get a doubt here. What is that? It's okay, sir. Just we are increasing the temperature. How much volume it is going to be increased? For example, initial volume of the gas, what we have taken, that will be V0. Okay, let us, we are observing the volume of the initial gas is how much? V0 will be. That V0 we have taken. For example, one gas is there at constant pressure, that gas is taken, and the initial volume of the gas will be what? If we'll increase the temperature of 3 degree rise in temperature, how much volume is going to be enhanced? V0 by 273. If we will raise the temperature of 1 degrees, at that time, what will happen? Whatever the initial volume, that will be as it is, it will be present. For example, V0 volume, if we have taken, that V0 volume will be V0. It should be there only. And how much it is enhanced? Whatever the amount of the volume we have initially taken, that V0, by 273 we did, the volume extra what we will get, that should be added for the original volume. So this is the increased volume for that. V naught by 273 into T it will be. So that's what V is equal to. That is the increased volume by increasing the temperature T degrees centigrade. That V is equal to V naught by V naught plus 273. That means what if the original volume of the gas will be 0 degrees centigrade. So V is equal to V naught of 1 by T plus 1 plus T by 273. That V naught, if we have taken common this, we have got here V is equal to V naught by 273. Water it will be T is equal to 273 plus T capital T it will be. So for a given mass, if we have taken V naught by 273, we are going to get a constant value. Then V is equal to K into T. So if we have taken that, what there is a relationship between volume and the temperature T will be, we'll see that V is equal to KT will be, where K is a constant, and we'll get a relationship from the above equation, V proportional to T. V is equal to KT or V proportional to T, and V by T is equal to K. This is called as what? Charles law. This is called as what? Charles law. So Boyle's law and Charles law both we have discussed. Once again, I will say the Charles law. It states that the pressure remains constant. The volume of a fixed mass of a gas is directly proportional to its absolute temperature. It will be. This is called as what? Charles law. This is the second law. In gas laws, this is the second law. So one problem we'll see in that what related to the Charles laws. Okay, fine. Then I'll see here what he's asking. With 2 liters of air, he's saying. So the question is not total question is not here. So on a ship sailing a Pacific Ocean where the temperature is 23.4 degrees centigrade, a balloon is filled with 2-liter air. What was missed here? Once again, I'm reading the question. Properly listen, children. On a ship sailing in a Pacific Ocean where temperature is 23.4 degrees centigrade. So initial temperature, it was not mentioned here. That is in the problem. Initial temperature is how much? 23.4 degrees centigrade. At that time, what is the volume of the air in a balloon? That is 2 liter. At 23.4 degrees centigrade, the volume of the balloon, it will be 2 liter. And what will be the volume of the balloon when the ship reaches Indian Ocean? So from Pacific Ocean to the ship is going to be reach Indian Ocean. Temperature is given, initial temperature, that is 23.4, T1 will be, and volume V1 will be 2 liters will be. Okay. And when it is reaches the Indian Ocean, where the temperature is how much? 26.1. T2 is equal to how much? 26.1. And he is asking us alone. That means V2 he is asking. V.4 when it is and T1 it is there 23.4, T2 it is there 26.1, V2 when it is reached to the Indian Ocean, he is asking the value will be V1 we have, T2 is in degrees centigrade, T1 is in degrees centigrade. We are converting it to the Kelvin by addition of 273. We are getting 299.1 Kelvin, that is T2, and T1 is 296.4 Kelvin will be. From Charles law, if we'll see that V is proportional to T means that is V1 by T1 for both. We can apply this formula. V1 by T1 is equal to V2 by T2 it will be. Then V2 is equal to what, children? V1 T2 by T1. Okay. So what is V1 initial value? Already it is there in 2 liters it will be. Okay. 2 liters we have taken. And after that T2 is how much? 299.1. So 2 liters and 299.1 by T1 how much? 296.4. So by doing the simplification and the calculation, we're getting as what? 2.018 liters it will be. So the question is here with 2 liters of air it is there. Before of that what? When it is under Pacific Ocean, the ship is in Pacific Ocean, at that time the temperature will be 23.4. It was not here. Okay, you can observe this one. T1 is equal to 23.4 billion. So this is what based on the Charles law, we have the problem here. So we have completed as what a Boyle's law and as well as a Charles law. The first law is Boyle's law. The second law we got as what a Charles. And now we're discussing about as what a Gay-Lussac law. The relation which between pressure and temperature. Boyle's law, and V is proportional to T, which is called as what uh, Charles law. Now the third law is what Gay-Lussac law. That's law is what Mr. Joseph Gay-Lussac, and he proposed that law. It states that what at constant volume, the pressure of a fixed amount of a gas varies directly with the temperature at constant volume. So continually you observe, children, in case of Boyle's law, what is constant? Temperature is constant. Then what are the variables? P and V. So PV are the variables and T is constant. Whereas in the case of Charles law, Vt or variables, P is constant. And in case of Gay-Lussac law, Pt or variables, V is constant. In these three, what? One is constant and the remaining two are variables will be. That we need to observe here. So what he's saying, at constant volume, at constant V will be the pressure of a fixed amount of the gas, that is P, varies directly with the temperature. That is mathematically directly with the temperature means P is directly proportional to T. So then P by T is equal to what? K, and P1 by T1 is equal to P2 by T2 will be. And whatever the graphical representation curves, if we have drawn in case of this, in case of Charles, in case of Boyle's, it was not mentioned in the slide, but I'm remembering once, if we have taken Boyle's law, at that Boyle's law situation, what is constant? Temperature is constant. So whatever the curves we have drawn, the graphical curves what we are getting in the Boyle's law, those are isotherms we can call. What we can call? Isotherms. Why? Because constant temperature we are drawing the curves. Similarly, if you have taken Charles law, at a constant pressure we are drawing the curves. Those are isobars will be. Now, what at a constant volume we are drawing the curves in between pressure and temperature. If we have seen that graphical curves can be called as what isocores will be at constant volume. At constant temperature, isotherms we can call. At constant volume, isocores we can call. At constant pressure, we can call isobars will be. So this is a Gay-Lussac formula. That is the third gas law will be. And one more law we are having, that's relationship between volume and amount. Okay, so what is the relationship in between V and N? If we'll see, this is called as Avogadro's law. The Italian scientist Mr. Amedeo Avogadro, he states that law. And what is it? If we'll see, it states that the equal volumes of all gases under the same condition and temperature and pressure contains equal number of molecules. This means that what? As long as the temperature and pressure remains constant, if the temperature and pressure remains constant, the volume depends upon the number of molecules of the gas, or in other words, if we'll say that the amount of the gas, mathematically, if we can write it as what V proportional to N will be. That is what V proportional to N means. While removing this proportional symbol, we will get a constant, that is V is equal to K into N. But N is equal to M by M, it is given. What is N is equal to M by M? Small n is equals to number of moles is equal to mass by molar mass. Small n is equal to what? Mass by molar mass of the gas what we have taken. That's why small m by capital M is given. Once again, I'm reading the law once you see clearly. Say that equal volumes of all gases, and any gas if we have taken in equal volumes, under the same conditions. What are the conditions? The temperature and pressure will be same for all the gases. Any other gases, if you have taken, the volume of the gases will be equal. And every gas contain equal number of molecules is saying. Example, if you have taken, Avogadro number of molecules will be present at STP, where any gas can occupy 22.4 liters. It contains Avogadro number of molecules. So this it represents that especially. So V is proportional to N, V is equal to K into N, but in place of N, we are going to write it as M by M. Why? Because number of moles key formula. That formula will be what? N is equal to small m by capital M. Small m is mass and a capital M is the molar mass. That's why what V is equal to K as it is we have written here. In place of N, we are going to write as what? Small m by capital M. That is V is equal to K into M by M will be. So this is what Avogadro's law. So this we can write it with another formula will be what? M is equal to, in place of that what D is equal to, we have the equation of what? Density is equal to mass by volume, it will be there. So this, if this M will come this side, it becomes what? Capital M is equals to, if small m will come this side, V by M it will be. And that is what K is a constant. So we can write it as what? Capital M is equal to K into D also. One more format we can write it. It's not a problem. It is not mentioned. Okay. So with this law, we have completed almost 4 laws. Boyle's law, Charles law, Avogadro's law, and Gay-Lussac law. 4 laws are finished. Okay, children. Right. Let we'll go with the next slide. So 4 gas laws are completed. The next ideal gas equation it is here. So once again we are watching that to get an ideal gas equation from these 3 laws. We'll get an ideal gas equation. How it will be? At constant T, V is proportional to 1 by B, or PV is proportional to 1 by, which is called as Boyle's law. At constant P, and it will be, for example, and at constant P and N, we are having V proportional to T, which is called Charles law. Already we have seen. And Avogadro's law, V is proportional to N. So based on these 3 equations, directly we can write it as V is proportional to, this will be there, V is proportional to N. That's why this we have written, V is proportional to N. And V is proportional to T, capital T, Charles law here. So V is proportional to N and V is proportional to T, we have written. And from the Boyle's law, V is proportional to 1 by P, it is denominator. So P is acting as a denominator here. V proportional to NT by P, it is there. So V is equals to, if we are removing the proportional symbol here, NT already it is there, and we are taking a universal gas constant, that is capital R, then it is RNT by P, it is there. Then P, if it will calculating, this is coming this side. So PV is equal to nRT, which is called as an ideal gas equation, which is called as what? Ideal gas equation. This manner we have discussed ideal gas equation. Okay, children. After that, so now we are entering into the questions manner. That means what? We are discussing questions right now. We'll see here the constant quantity of Boyle's law is. So in this class, he may ask what, which is the constant factor, which is the constant measurable property, and which is the variable measurable property will be. That he wants to ask here. So we need to know the concept, which is constant, and what are the measurable properties in each gas law, that we need to know clearly. Okay. So based on that, if we'll see the Boyle's law is what? P is proportional to 1 by V will be. That we know that at constant what? At constant T. So temperature is constant. Okay. And N is also constant, it will be. We'll see here the options he has given as what? The constant quantity of Boyle's law will be. What he has given? Constant quantity of Boyle's law, if we'll see, only mass of the gas he is mentioned, only temperature of a gas he is mentioned, mass and pressure of the gas he is mentioned, mass and temperature of a gas he is mentioned. So clearly we know that at constant temperature and a fixed amount of the gas we mentioned in the Boyle's law. So we can say that as what? Mass and temperature of the gas is the correct answer itself. Okay, children. After that, then if we'll see, next one is what the next slide, if we'll go with that, what is the nature of the pressure volume graph in Boyle's law? So he's asking us what? Straight line, circle, elliptical, rectangular, hyperbola he is given. Okay. We'll see PV graph in the Boyle's law. It is a rectangular hyperbola. Why we are getting a rectangular hyperbola? So based on the concept, based on the law, if we'll discuss here, while increasing the pressure, the volume is going to be reduces. That means what? The pressure increases means what will happen? Volume is slowly decreases like this. So the graph will be like this. The graphical representation is also there in another slide. I'll explain that also. So the graph will be like what? A parabola, hyperbola will be. So rectangular hyperbola, that is what like this. So it will be start. While increasing the pressure, the volume, so slowly will increase the pressure like this, and the volume will be decreasing like this. That's why what we are going to get a rectangular hyperbola will be. So the answer is what? It's not a straight line, it's not a circle, it's not an elliptical path. And the relation he's asking in between P and V only. Different graphs will be there, P and 1 by V. So those are different, it will be. So in between P and V, if we have taken the graphical representation will be what? Rectangular hyperbola will be. Okay, children. After that, next slide, if we'll see here, the state of the equation for 7 grams of oxygen gas is he's asked. So we know that ideal gas equation is what? PV is equal to nRT. PV is equal to what? nRT will be. So the option is given as what? PV is equal to 7RT, PV is equal to 32 by 7RT, 7 by 32 RT, PV is equal to 32 RT. So the solution, if we'll observe, 7 grams of oxygen he is saying, it is a mass, that is small m, it will be how much? 7 grams. And oxygen molar mass is how much? That is O2. O2 in the sense nothing but 16 plus 16. So 2 oxygens will be there. For each oxygen 16 grams it will be. The molar mass of oxygen is 32 grams. Everybody knows it. And PV is equal to nRT is the formula. So but n is equal to, we know that number of moles equal to small m by capital M. That's what? 7 grams by 32 grams. 7 grams by 32 grams here. Hence PV place of PV it will be there. In place of n, what we can write? 7 by 32. RT both are constant. One is universal gas constant. It will be, it is temperature. No other values are given in the problem. That's why what? PV is equal to 7 by 32 RT. So clearly it is representing as what? PV is equal to 7 by 32 into RT itself. It is there. Okay, children. All right. We'll go with the next question. What is that? If the pressure of a certain amount of a gas is reduced to 1 by 4th of its initial pressure at a fixed temperature, then what would be its final value, he is asked. So clearly observe, children, there is no confusion in the problem. Clearly, we need to know from the given data what is P1, what is V1. We need to know that. If we'll know clearly, we'll apply in the formula, we'll get the question, we'll get the answer easy. We'll see. If the pressure of a certain amount of a gas, so initial pressure you can consider as P. Initial pressure we are considering as what? P will be. Okay. Initial pressure P1 equal to P. So P1 you are considering what a P will be. Okay. After that, if the pressure of a certain amount of the gas is reduced to how many times? 1 by 4th of its initial pressure. Initial pressure, how much we have taken? P is the initial pressure. And it is reduced to how much? 1 by 4. So P1 will be P and P2 will be P by 4. That is P by 4. And P by 4 it will be there now. That 4 will come on to the top. It's become what? That 4 into P it becomes. So P1 in the place of P1 what will get? 4P by, and P2 we are getting as what? It should be P2 should be P by 4, but 4 is coming into the numerator. That's why what we are getting? P1 by P2 is equal to 4P by P. It is there. Then what would be its final value, he is asking. And says here, so we don't know both the values. Yes or no? So that's why what? Directly we are writing as like the formula with a Boyle's law. P1 by P2 is equal to V2 by V, and that we know that. We'll see here V2 by V1 as usual we have written. Why? Because we don't have any other values of gas. So because of that reason, 4P by P is equal to V2 by V1. As it was mentioned, initial pressure is P and it has reduced up to 1 by 4 because P by 4 we have taken. So 4P by P. PP gets cancelled and V2 by V1 is equal to 4. It will be there. So V1 will come this side, V2 will become what? 4V1. So this volume, it becomes what? 4 into initial volume times the second volume. So once we'll reducing the pressure, the volume becomes of what? 4 times of its initial volume. If we will reduce the pressure of its initial pressure, the volume becomes with its 4 times. The volume becomes with its 4 times of its initial volume. That's why we are taking the option as what? 4 times. That is C is the option, children. Okay. After that, the next question is what? If we have seen, at which condition the real gas deviated from the ideal gas behavior. So from the ideal gas behavior, this we need to remember as what? At high pressure and low temperature condition, any real gas deviated from the ideal gas behavior. The real gas can deviate from the ideal gas behavior at which condition? At very high pressure, at low temperature, there is a chance of deviating of a real gas can deviate from the ideal gas behavior. Okay, children. So the remaining questions tomorrow we'll discuss in the tomorrow class. In the next class, we are going to discuss about what? Remaining topics and remaining questions will be Okay, thank you.